All right, today we're tackling a big one, the illusion of deep learning. Can AI ever truly learn? This is all based on a really fascinating new research paper that introduces a concept called nested learning, and it gets into one of the biggest questions in the entire field.
So let's start with this really weird paradox, right? Why can't the smartest AI in the world learn anything new? I mean, you've got these incredible LLMs, large language models, that can write poetry, spit out code, answer questions that would stump most of us. But, and this is the big but, once their training is over, that's it. They're basically frozen in time. They can't actually learn from new conversations or experiences. So what's going on here?
Okay, so here's how we're going to break it down. First, we'll dig into that AI learning paradox and a really cool analogy called digital amnesia. Then, we'll see what the human brain can teach us, introduce this new idea of nested learning, check out a new architecture called HOPE that puts it into practice, and finally, we'll wrap up with what this all means for the future of learning.
All right, Section 1, the AI learning paradox. For years, the main idea in AI has been simple. Just go deeper, add more layers to the neural network. But it turns out, just stacking more layers isn't always the answer. It's not the silver bullet we thought it was.
Here's the thing about today's LLMs. They're powerful, but they're completely static. Think of it like this. All their knowledge is locked in a vault the moment their training ends. When you give them new info and a prompt, they can use it for that one conversation, sure. But the second you start a new chat, poof, it's gone. It never becomes a permanent part of what they know.
And just making these models bigger and deeper, well, it doesn't really fix the problem. The paper points out a few reasons why. For one, more layers doesn't automatically mean more computational power. Sometimes it just makes training messy and inefficient. But the real kicker is that it just doesn't solve the core problem. It can't help the AI adapt quickly to new tasks, and it definitely doesn't enable what we call continual learning, the ability to learn and grow over time, like we do.
Okay, so to really help us get our heads around this, the paper uses this absolutely brilliant analogy from neuroscience. It frames the whole problem as a kind of digital amnesia.
I mean, look at the difference here. Our memory is dynamic, right? It's always changing. We have new experiences and our brains turn them into long-term knowledge. We adapt. But in LLM's memory, it's frozen. Its long-term memory is just that giant pile of data it was trained on. And its short-term memory, well, that's just the stuff in your current chat window. The moment that window closes, it's gone.
The paper actually gets super specific and compares it to a real neurological condition called anterograde amnesia. You might have seen this in movies. It's when a person can remember everything from their past, but they can't form any new long-term memories. Every new experience just vanishes. And that is a perfect description of today's LLMs. They have this digital form of amnesia. You can feed them new information, and they can use it for that one brief moment. But they can never, ever consolidate it into their core knowledge. It's like they're permanently trapped in the now of their training data, unable to build a future. So if the problem looks like something from a neurology textbook, maybe the solution does too. And that's exactly where the researchers went looking for answers: the human brain.
Turns out, our brains are way more complex than just a single learning system. We basically have these two processes that run at totally different speeds. First, there's a super fast online phase called synaptic consolidation. This happens right after you learn something new, just to stabilize the memory. But then, there's a much slower offline process. This is systems consolidation. This is the deep work, often when we're sleeping, where the brain replays and reorganizes those memories to lock them in for good. And this is the key insight, right here. The reason we can keep learning our whole lives is because our brain uses processes that run at different speeds. It turns these fleeting experiences into permanent knowledge. And this whole idea of different learning speeds, it's pretty much completely missing from how we build AI today. Which finally brings us to the main event, introducing nested learning. This is the paper's big idea for giving AI a new dimension of learning. To get there, the paper starts by redefining some terms. Check out this quote. Memory is a neural update caused by an input, and learning is the process for acquiring effective and useful memory. So it's not just about cramming data in. It's about how the system updates itself to create useful memories. That little shift in thinking is huge. So what is nested learning? Well, the paper gives us a great metaphor. Instead of thinking of an AI model as a stack of pancakes, just one layer on top of another, think of it like a set of Russian dolls.
Each stall inside the other is its own level, its own optimization problem. And here's the cool part. Each one learns at a different speed, a different update frequency. And to show this isn't just some crazy abstract idea, the researchers point out something really clever. We're actually already using a simple version of this. Think about a standard optimizer, like gradient descent. That's a simple one-level problem. But what happens when you add momentum to it, which we do all the time? Well, that's where the aha moment comes in. Suddenly you have a two-level nested system. The momentum part acts like a fast inner memory that learns from the last few steps to help guide the slower outer update of the main model. It's been hiding in plain sight.
So yeah, this reveals that even the standard tools we use are basically these simple two-level learning modules. We've been doing it by accident. Nested learning is all about making this explicit. It's about intentionally designing these levels to be more powerful and to work together.
Okay, so this all sounds great in theory, but does it actually work in practice? Well, that's what the next section is all about. The researchers built a brand new architecture called HOPE to put this whole idea to the test. So what's HOPE all about? It's built from the ground up on these nested learning principles. It has what they call a continuum memory system. Basically, different parts of the model, these MLP blocks, are designed from the start to update at different speeds. The whole goal is to create a system that can actually modify itself, one that can continually learn.
And the big question, does it work?
Well, take a look at this. This is a quick snapshot of its performance. And yeah, the results are really promising. The 1.3 billion parameter version of HOPE is right up there with other top models, and on average accuracy, it's actually pulling ahead. Not bad at all.
So what this tells us is that this isn't just some interesting theory. HOPE is a real, concrete step toward building AI that can modify itself. It's a proof of concept that we might finally be able to build an AI that can learn continually.
Okay, so let's zoom out and think about the future. What does all this mean for the future of AI? Well, it suggests we might need a pretty fundamental shift in how we think about building these things.
The big idea here, the main takeaway from this whole thing, is this. The next big breakthrough in AI might not come from just adding more layers, from making models deeper. It might come from adding more levels. These nested levels of learning that all operate at different speeds. It's about moving from a stack of pancakes to a set of Russian dolls, creating something that looks a lot more like our own brains.
And that brings us to one last thought to leave you with. Imagine for a second that we actually pull this off. We build an AI that can learn continuously, just like us. What would be the very first thing you'd want it to learn? Something to think about.